Hey everyone, and welcome to RUBIN'S Mind Lab, where we break down the latest research into what it really means. Ever wonder if talking to a computer can really tell us what a person is thinking or feeling? Well, this new study dove deep into using super smart computer programs called large language models, or LLMs, as digital twins for people. And they asked a big question: can these computer twins really act like us in psychology studies? Now, when scientists do studies, they need to understand something called the construct validity. This is a fancy way of saying a study needs to actually measure what it claims to measure. Think about it. If you have a ruler that is bent, it is not going to accurately measure length, right? The same goes for psychology. The researchers here wanted to know if LLM twins are accurate rulers for measuring human thoughts and feelings. They looked at two main things: construct representation, how the LLM understands a concept, and the nomothetic span, which is how the LLM's understanding relates to other known factors. Just like in a person, they treated real human answers as the gold standard. The researchers used LLMs to generate answers in place of real people for things like public opinion polls and psychology tests. They wanted to see if these LLM twins could give us the same kind of information as real human participants. Early research showed mixed results. Sometimes LLMs could copy big patterns like matching average opinions or showing how certain psychology experiments work. But other times, they didn't show the same variety of human behavior, gave answers that were too similar, or just gave the most correct or common answer. This led to the main question: can LLM twins be truly compared to humans in terms of their psychology? So they set up their research to check for construct validity. A big risk here is that LLMs and humans might seem to give similar answers, but from totally different internal processes. Human understanding is built on real-world experiences and talking with others. LLMs learn by finding patterns in huge amounts of text. So even if an LLM says something that sounds right about, say, aging, it might be thinking about it in a very different way than a person does. It is like speaking the same language but having completely different dictionaries. This can lead to what they call unintended confounding. For a person, things like age and sex can influence their attitudes, but for an LLM, these are just cues in the text. Changing one cue might accidentally bring up other ideas the LLM learned are connected in text, even if they shouldn't be related in the real world. This can make it hard for the LLM twin to isolate and measure just one concept cleanly. To figure this out, they designed a pipeline where survey answers and personal features go into the LLM, which then builds a twin of the individual and gives responses. They then checked if the relationships between these inputs and the outputs in the digital twin were similar to the relationships seen in human. They ran 4 main studies. The first one looked at word associations to see if the LLMs organized concepts like humans do. The second study tested how well the digital twins performed on decision-making tasks where humans have known biases. The third study explored how much personal information was needed for the twins to accurately represent Big 5 personality traits and how well these traits related to other measures. The fourth study looked at how LLMs express themselves in free text writing in both English and Chinese, checking both the language style and the psychological themes. In the first study on word associations, they found humans had fewer words overall, but a wider vocabulary. The LLMs were more likely to give an answer for every word cue, but they didn't cover as much ground with their vocabulary. When they looked at the connections between words, human and LLM networks were quite different. LLMs missed many human-specific words. Even the global structure of these word webs showed differences too. Humans' word webs had higher centrality, meaning some words were more central or important in human thinking than in the LLM's community analysis. Showed some overlap in how LLMs and humans grouped words, but it was only partial. And when they looked at how these association spaces predicted external measures like emotional tone or concreteness of words, human spaces consistently gave better predictions than the LLMs. So while LLMs do capture some semantic structure, it is not quite the same as how humans organize meaning in their minds. This suggests LLMs might be good for idea generation early in research, but they need careful human oversight. In the second study, they tested digital twins on classic psychology tasks that reveal how people make decisions, often with biases. Across many tasks, the LLM twins were generally accurate, and individual response profiles were pretty well correlated with humans. However, when it came to specific cognitive biases, the LLMs often acted more like perfectly rational economic actors than humans. For instance, in probability matching, humans chose the maximizing option only 30% of the time, but the LLMs did it almost all the time. They showed little sensitivity to anchors in calculations, sometimes got the factual answer perfectly, and missed several framing and sunk. Cost effects, omission bias, where people are more hesitant to act when there is a risk of harm from action compared to inaction, was also significantly weaker in LLMs. This suggests that while LLMs can be accurate, they lack the bounded rationality that drives many human judgments. They don't have the same cognitive limits or biases that come from fast, intuitive thinking versus slower, deliberate thought or from real-world experiences. The researchers suggest this might be due to how LLMs are trained to prioritize correct or helpful answers, potentially suppressing more intuitive or biased human-like responses. In the second part of Study 2, which looked at temporal validity, they found that adding survey dates or information about what was happening at the time did little to improve the LLM's predictions. Even though the models seemed to understand the temporal information, they didn't give it much weight in their answers. This highlights that LLMs might average out historical information and struggle with the nuances of time-sensitive and uncertain contexts that shape human responses. Study 3 focused on predicting Big 5 personality traits. They found that the psychological relevance of input information was more important than just the amount of information. Providing features that were highly correlated with the personality traits worked almost as well as giving all the information. Demographics alone weren't very helpful. Network analyses showed that richer inputs improved the digital twin's ability to replicate the expected 5 community structure of the Big 5 traits. However, there were still deviations and differences in item loadings, meaning the same personality score could be reached through different item relationships in humans versus the LLMs. This is a key point for measurement equivalence because the overall score is similar doesn't mean the underlying measurement structure is. They also explored statistical calibration techniques, finding that correcting for bias could improve some metrics but didn't fully restore individual variance or solve all the discrepancies. In the fourth study, they looked at free text responses in English and Chinese. Across both languages, human and digital twin texts had distinct differences in their surface style. Humans used more named entities and had more variable sentence structures. Digital twins, even with richer input, often had lower named entity density and more compressed sentence patterns. When it came to psychological construct representation, the meaning conveyed at a broader level, richer features did help digital twins get closer to human semantic distributions. However, the individual writing style, the surface form, remains non-human-like and insensitive to richer profiles. This suggests LLM twins might be better for understanding what is being said at a concept level than how a specific individual writes. So, to wrap up, this research makes it clear that LLM-based digital twins are not perfect copies of humans. Surface human likeness can be deceiving. There are two main points of separation. First, LLMs and humans organize meaning and associations differently in their minds. Second, person-specific information gets processed differently. For humans, it is lived experience. For LLMs, it is textual cues that can activate broader, unintended associations. The findings support a conditional view of digital twin validity. They're most useful for broad semantic structure, individual response profiles, and general relationships between constructs, especially when given rich, relevant information. However, they're less reliable for fine-grained item details capturing human heterogeneity. Understanding bounded rationality or biases, dealing with temporal changes, or ensuring measurement invariance. Their validity really depends on what you are trying to study and how precisely you need to measure it. The researchers offer a set of recommendations to help guide the use and validation of LLM digital twins. Essentially, they're saying we need to be very clear about what we expect from these twins and rigorously test if they meet those specific expectations. They can be powerful tools, but we need to understand their limits to use them wisely and ethically in psychology research. What are your thoughts on using LLMs as digital twins? Let me know in the comments below, and if you found this breakdown helpful, don't forget to like this video and subscribe to RUBIN'S Mind Lab for more explorations into the fascinating world of psychology.